Yeah. Our first talk is by Ahmed Touati. Ahmed is a research scientist at FAIR at Meta. He has completed his PhD working on reinforcement learning. He has developed the forward-backward approach for unsupervised reinforcement learning and is one of the key proponents of zero-shot reinforcement learning. These algorithms have been behind the recent success of MetaMotivo, a humanoid agent that can be controlled to do a whole sort, various sorts of whole body manipulation tasks. Today, he'll be talking about bootstrapping reinforcement learning, pre-training RL agents through RL.
Or it's connected to okay. And I think we don't put the audio. Okay. Okay. Yeah.
You're sharing it on Zoom?
No, no. Share from Zoom?
Yes. Perfect. Yeah, this is.
All right, please. Sure. No worries, wait. Okay, all right. Yeah, thanks for the invitation. Thanks also for the introduction. Yeah, so in this talk, I'm going to talk about how to, like, some approaches to pre-train a reinforcement learning agent using reinforcement learning itself. Why I'm talking about this is just to contrast a bit, like one of the main approaches nowadays, like which consists of collecting a lot of expert demonstration and then doing like more behavior cloning supervised learning. And this, for example, have been successfully implemented in, for example, PyZero or Gemini robotics. And for example, if you look at the technical report of Gemini robotics, they are mentioning they spent like 12 months of collecting expert demonstration to be able to have like this robot that doing a lot of manipulation tasks. And here in this talk I'm gonna more like focus on other approaches that uses more like reinforcement learning to do pre-training. Yeah, so this is the outline of the talk. So first, I'm going to just introduce the setting of the zero-shot controllable agent and also explain what we have done so far. Then I'm going to explain how to pre-train representation skills to build like a zero-shot controllable agent. And at the end, I'm going to talk about how to learn a Bootstrap word model to be able to do planning and optimize at test time. So yeah, so this is the setting. So imagine you have an environment in which you can perform actions, but you have no reward signal. So we have only like reward-free interactions, and this can be like either online or actually you can leverage also like offline data that's generated by other behavior policies. And our mission is to build a summary of the environment such that at this time As soon as I describe the reward function to the agent knows what to do to optimize the reward function. So in other words, we would like to build a compact object that store all the planning solution of the MDP, and then we would like to have also an inference method that be able to query this compact object with the task specification and return a policy that is able to satisfy the task. So this is like a step towards building a fully controllable agent that is able to follow instruction in real time with minimum amount of additional computation, planning, or fine-tuning at this time. So I'm gonna give you an overview of what we have done, and then I'm gonna delve more into detail. So in terms of theory, we proved that there exists a representation of an environment on which we can directly read all optimal policy for of all reward functions. This is our paper back in NURIPS 2021. And we call this the forward-backward representation, FB in short. So this representation are learnable from reward-free interaction and can leverage off policy data. At this time, the task can be specified either as a reward function to optimize, a goal to reach, or a behavior to imitate. And also, like at this time, the policy can be obtained by an explicit formula. So we don't need any fine-tuning or planning at the first step. So in terms of more like experimental results, so we have shown for at least in the offline setting when we have like access to the data of exploratory transitions. And then we can train our agent in offline manner. You can see that actually when we test our agent on different tasks in each of this continuous control environment, our agent can very competitive to the single task TD3, which is like trained for each of these tasks individually. Whereas our agent is trained without any supervision of the task, but able to solve all these tasks.
That's feedback.
Yeah.
Do you want to pick this up?
Okay, so okay.
Is this better?
Yeah, I think so.
Okay.
Thanks. Yeah, also we like with this paper, like 2 years ago, also like we released this funny demo. So we have like a worker agent that is pre-trained in unsupervised way. And here actually we offer to the user to type a formula to express the reward function that he would like to optimize. And then actually you can see the rollout from the actual policy. And this is like a really zero shot. And you can like modify the reward function. So actually you can see the zero shot aspect in real time. After that, we wanted to scale up more this approach. So last year we tackled this whole body humanoid control. And we wanted to have an agent that is also like very versatile and can express many behaviors at this time. And to do this, so actually we train our agent, like a modified version of our agent on a mixture between motion capture data and online interaction with a simulator. And then once the pre-training is done, so we have a frozen agent that actually can does all these tasks. And all these tasks, for example, can be expressed as a formula, as a reward function, or it can be, for example, goal to reach or motion to track. And also, like by the end of last year, we also like released this Metamotivo demo. So it's an interactive demo where actually you have an agent, and then you have like 3 modality of task specification that you can precise. So for example, you can precise a motion to track. You can precise here, for example, you can also like type your own formula. It's like in the worker demo before. And you can also like precise position or goal reach. And because also like it's interactive, so actually you can also like interact with him with the agent. For example, you can for example throw balls on the agent. You can also like create some wind velocity, and also we can also like vary the gravity, and all those variation of the environment is not something that the agent is trained with, but actually the agent is able to be robust and able to manage to keep doing the task while actually they're doing enforcing all this adversarial parameters. And yeah, by the way, actually the demo is online, and you have code and models and that. Okay, so let's go back to fundamental nodes to explain a bit more the approach. So fundamental quantity that we leverage here is what we call the successor measure. So the successor measure is of policy answers the following question. If you start at a state S and then action A, and then you follow for your policy, where do you spend your time? And formally speaking, this can be written as the sum of discounted probability of reaching state at critical times that T in T, conditional on starting the state and actions and the policy pipe. And actually in discrete state space, this is what we call successor representation, and can be written as a value function, where the reward here is the indicator function. And the main idea of our approach is actually this finite rank decomposition of the successor measure. So we're going to train a representation F and D to approximate the successor measure. So here F stands for the forward mapping, and we call it forward because actually you can see it as encoding state and action in the future in the latest space. And B is a backward that encodes the past of the state S prime. And the training criteria is if S and S prime are reachable eventually in many steps, then actually I would like their embedding F of S and B of S prime to be aligned, and actually to encode exactly this likelihood of reaching the state S prime starting by the initial state S. And why actually this is very useful? Because this is actually enables zero-shot policy evaluation. So we know, for example, the Q function. So if I take your fixed policy pipe, I know that the Q function can be expressed as the reward of the state, where the state is weighted, the reward weighted by the successor measure. And now if I replace the successor measure by its lowering decomposition, now I can write all the Q function as an inner product between the forward mapping and the vector ZR. And the vector ZR here can be expressed as the expected backward embedding weighted by a reward function. In other words, this can be seen as the orthogonal projection of the reward function in the linear span of P. And Z is just a vector of P dimensional. This is leads me to the definition of the algorithm itself. So the idea here is actually we're gonna generalize this low rank decomposition to continuous set of policy parameterized by the latent variable Z. So we're gonna learn two representation F. Now it depends on certain action, but depends also on Z. So we have an additional parameter as input of Z, because now F is going to encode the future of the state, but also depends on the policy Z, and V is still going to be just a state embedding. And when we say that FV is a forward backwards representation, if FV approximates the successor measure M by Z. But here we introduce also like the policies, because before we were just talking about the fixed policy pipe. But here we're gonna also learn jointly representation, but also like policies, and those policies are gonna be parameterized by the same vector Z and are defined as the greedy policy with respect to f.z, which is actually the Q function of the latent task Z, as we showed in this slide before. So you can see FB is gonna provide an occupancy map over states for various behaviors. So this is a way to encode like long-term relationship between states. And it's also like word model light because given state and S prime, it's gonna give me what's the likelihood to reach S and S prime condition on some policy pi, but it doesn't need to do any trajectory generation or synthesis of states. And the main theoretical result here we have is if now I have this definition of FB and I managed to train it perfectly. Now for any at this time for any reward function R, if I project my reward function on the linear space of B, this can be done in closed form by this formula. So with just the R equals the expectation of B weighted by the reward. Then actually the policy pi z R is guaranteed to be optimal for the reward R. So far, you can see like the definition of FB doesn't involve any reward function. So actually, we can pre-compute all these representations and policies without knowing the downstream task. And at this time, we can extract the policy in closed form. So for example, if you have a goal-reaching task, when the reward is just an indicator on the goal state, so the vector ZR is going to be B of the goal state. If I have a general reward function, I just have to estimate this expectation by an empirical average of B time R. And for the training loss, because so far we just talked about the definition of FB, but also we can now how we train this. So we know that I would like that FP approximate the successor measure MPI, but we know actually also like that this MPI satisfies a Bellman equation. So actually I can train FB by minimizing the steady error. So so here the loss is an expectation over the latent variable C, latent task, and would like to minimize this TD error. So here the loss is you can see in discrete state you can see it's like a rule-weighted weighted version of Frobenius loss over matrices. But this loss actually is not very practical because you can see like the first term of the Bellman backup is actually P, which is actually the one-step transition matrix that we don't have access to it, especially if you have like continuous state. But actually, you can show that this loss and practical loss can be devised into like sample-based loss, whereas in the final loss it's going to be like contrastive loss that is conditioned on the policy pi z. So in practice we just sample transition state action and the next state, and then we're gonna sample z variables per transition. And then I will construct this big matrix of number of rows is going to be the batch size, and column is going to be a batch size as well, where actually I'm going to compute all the pairwise inner product between F and B. And then for the diagonal term is going to correspond to inner product when actually I'm taking F of S and B of the next state. So I would like to minimize, I would like to maximize the alignment between these two vectors because I know that S prime is in the trajectory of S. So this is give me this diagonal term in blue where actually I'm minimizing the minus of the inner product. And for the off diagonal term, I'm just gonna do bootstrap. So I'm gonna bootstrap the estimate of the successor measure in the in the next state. Okay, so so far this can be trained more in offline setting where we have like a data set of good coverage of state and action. Okay, how to scale this? And this is something we tackled in the project of last year. Where we wanted to create this like zero shot whole body humanoid control. So what's the challenge in humanoid control? So if I do just online interaction with unsupervised exploration, most of the time actually my agent is gonna fall down and actually does something not very interesting. because I don't have any like supervision. And even also actually if I have like a reward function that I would like to optimize, and for example, I optimize this agent using TD3, the produced behavior are very unnatural and not human-like, because actually the agent is gonna start to hack the reward function and gonna discover something that actually maximize very well the reward, but actually it's visually doesn't look looks good. So that's why in this project we're gonna leverage motion capture data. So motion capture data are just recording of human activities. So we have a sequence of joint positions of many behaviors. For example, dancing, walking, jumping, etc. And those usually those data are very unstructured, so we don't know actually what's the behavior displayed if we don't really render it and see the corresponding behaviors. So the idea of the algorithm is we would like to learn with online interaction, but also we would like our discovered behavior capture the behavior that exists in this motion capture data. So to do this, first of all, we have to have a way to characterize what I mean by behavior. So for the discovered behavior, that's actually the behavior that are discovered by the agent, this is actually pretty easy, because actually I can represent those behavior as a joint distribution of Z and S, when Z is going to be something that I sample randomly from my latent space, and S are going to be the state that are generated by the policy by Z. But now I would like to do the same for the motion capture data. And the idea is like I'm going to take my data set of motion. I take a chunk of trajectories, so I take consecutive of states. So this will give me states, but then I have to embed this in the latent space. And the way we do this is actually we're doing this through actually the backward embedding. So we're taking just an average of the state that are in the sequence. And why actually this is good way to embed, because if you remember the formula that we use to infer the Z from a reward, this is correspond to having a reward function that is equal 1 for each state in the motion and 0 everywhere. So the policy that is encoded by this variable ZM is going to be is policy that's going to try to visit this same state and imitate the behavior. So this is give us a compact way also to represent the distribution of behavior that exist in those data set. And now the idea is very straightforward. So in FB, the representation part is going to be the same as I presented earlier, but we're going to just modify the policy learning part. Now the policy part is going to be combination weighted loss between the unsupervised objective and imitation objective. And the imitation objective here is just divergence between the joint distribution of S and Z of the discovered online behaviors and the joint distribution of state and Z of the data set, of the behavior that are in the motion capture data set. And of course, like decay divergence is not something tractable. So we're gonna do like adversarial learning. So we have to do learn discriminator that is conditional on state and Z and predict whether this state is a motion or actually it's a simulation state. This is gonna with this I can define a reward function, and then in the end the actual policy loss is going to be equal to the Q function of FV, of the unsupervised objective, plus the Q function of that coming from the reward of this discriminator. Okay, so this is actually the overall idea of the FB with conditional policy regularization. And in terms of result, I'm gonna skip this. But just like there was no existing benchmark, so actually we create our benchmark. So we have this human read, and then we define like 64 reward based tasks. around 1,000 motion for tracking, and also like 50 posts for Go reaching. For a numerical result, you can check the paper. Just here, I'm gonna show a bit of qualitative result. So for reward-based task, where here the inference is just you take you sample state from your replay buffer, you reward them, and then you compute the CR. So this is actually what FBCPR does, and this is for in contrast with TD3. Then they are having gets good reward, but TD3 just does like very unnatural behavior. For also like pose reaching, this is easy also as inference. We just do z equal to db of the goal. So this is like the pose that we would like to reach, and this is actually the actual policy, the zero-shot policy performance. And for the tracking motion, what I mean by motion tracking, so I have a sequence of state, and I would like to track them. So this can be tracked by non-stationary policy. So for each time step, I have to give to the agent the embedding of the next state to track. So it's like at each time I'm switching between policies. And this is enabled to have an agent that can be able to follow like very long motion. Okay, this is finished my first part. I don't know how much time I have. Maybe 10 minutes. Okay. So yeah, so far I talked about zero-shot controllable agent. I'm gonna switch the focus here, and the idea is like, okay, I have zero-shot. I have I have like good performance at this time, but can we do better? And the idea actually would like also to pre-train other components during the unsupervised phase that enable me to do also like optimization at this time, at inference time, so I can probably improve over this pre-trained policies. And to be able to improve over pre-trained policy, I would the idea is like actually I need to build like a word model that is describe the long-term behavior of this of the policies, to be able to reason about different policies and their different consequences, and take actions that maximize my return. So, okay, one way to do this, the classical approach to do this is actually I can learn the one-step word model. One-step word model, I take state and actions and predict next state or distribution over next state. And then because I would like to evaluate the policy, so I have to roll out this word model many times to predict the longest term future of a policy. But the problem actually, we know that this is not very efficient, because enrolling the one-step model can incur test time component error, and this is gonna limit substantially the effective horizon of downstream task I'm gonna consider. So a different alternative is actually learning what we call the geometric horizon model, or bootstrap word model. So what does mean? So I have actually, so it's very easy. It's actually a generative counterpart of the successor measure. So it's a generative model that enables me to sample from the occupancy of a policy. And why this is actually interesting, because I don't need, with such a model, I don't need to sample temporally consistent states. So I don't have this component error at this time. I just need to sample like many independent samples from the same model, and then maybe average them to get the reward. So I just need independent samples instead of doing autoregressive generation of samples. And the idea of this model is just gonna predict state at random time, where here the time is gonna be geometrically distributed. Okay, so this is very appealing approach, but actually very the existing one. If we try to learn this, a lot of existing methods actually fail really to train with gamma discount factor that's very big. And most of the time, they're just able to train with gamma equals 0.8, which means like just predict, I think, 10 steps in the future or something. So it's not enough. So that's why actually we in this project we call like a temporal difference flow. We try to leverage this new powerful geometric model such as diffusion and the flow matching to be able to learn such distribution. So I don't know if people are familiar with flow matching, but this is like a very short recap. So imagine I have like very nice situation where I have already actual trajectory from the agent. So from each state, I know already what's going to be the future of the agent. So in this case, I can use the standard conditional flow matching objective. So the training objective is easy if you know already like flow matching. So we have here VT is a vector field. It's not value function. It's a vector field which condition on state and action. I am gonna sample x0 from my starting distribution, which is gonna be noise, and then I'm gonna sample x1, which is gonna be a clean sample. So it's gonna be a sample from my actual trajectory, and then I will do interpolation between the noise and this clean sample, and I will train my vector field to predict the velocity of this interpolation. Because here the interpolation, this conditional probability path is like a fine interpolation. So it's 1 minus t, the noise plus t, the actual state. The velocity of this interpolation is just the tangent. So actually just the difference between the state and my noise. And to sample from my flow model, I have to numerically integrate the corresponding differential equation, and this can be done pretty efficiently with Euler approximation. So it's going to be like multi-step generation in this case. Okay, this is very convenient setting, but most of the time I don't have trajectory for my policy. I have just like random data set. I have transitions, but I would be able to leverage those transitions to build a geometric model of many policies. So we are like more in off-policy setting. And the idea how to do this is actually we're going to use again the Bellman equation satisfied by this geometric horizon model. So we're going to turn the flow matching objective into like an iterative objective, where each time I'm going to minimize the discrepancy between the current model and the bootstrap version of the model. So one way to do this, like the naive way to do this, is at each iteration of my algorithm, I have to create my target distribution, which is like a Bellman backup applied on my distribution. So what I do is like from my next state, I'm gonna sample a state from my current model, and then my x1, which is gonna represent the clean sample, is gonna be a mixture between the next state and this bootstrap sample. And then once I have my x1, I will do the same procedure of flow matching. So I will take a noise, and then I'm going to interpolate between this target sample x1 and the noise, and I will train the vector field using the conditional flow matching objective. The problem of this one when we try it in practice, this is an expectation induces a nice Bellman equation, and you can show that it's contraction, and actually you can really converge. But actually in practice doesn't work at all. Doesn't work at least when you scale the discount factor. So actually we came up with this new algorithm which is called t-square flow matching, whereas the idea here is it's actually we're going to leverage more information about our target distribution. I know my target distribution is actually a mixture between a one-step transition and a bootstrap term. So I'm going to use two different losses for each of this distribution. So the first one is going to be the usual conditional flow matching for one-step transition. And the other one is going to be the bootstrap version of flow matching, Where here I'm gonna bootstrap twice. I'm gonna bootstrap, so instead of predicting till the end my target sample and then doing interpolation, I'm gonna use actually the ODE path that is already learned by my model to predict to take state that are in the midway between the noise distribution and the final distribution. So I will stop my ODE sample here at xt instead of going to x1. And for the target of the vector field, I'm not going to use the only like the difference, like the velocity condition velocity, which is x1 minus x0. I'm actually going to use the vector field, the target of the target distribution. So this is in the end, it's like TD learning, but instead of value function, I have now vector fields. And the theory, we show that this objective can has much more variance for gradient estimate with respect to the previous one. And also, like if you are also familiar with flow matching, actually the probability path that induces by this method reduces the transport cost between the noise and the target distribution. And this is actually a very nice property for flow matching. Okay, so just finish by some experiments. So here just to show like an ablation on how far in the future we can predict. So all the other methods can incur a lot of error in prediction the value function when I scale the effective horizon of the prediction, while actually T-square FM can has like very moderate performance degradation, even if I predict like 100 steps ahead in the future. And more like qualitative results. So the naive TD flow approach can work well with small gamma, but then when gamma is very, for example, very large, like 0.99, you can see like we start to lose accuracy, whereas actually the square is able actually to recover the ground truth distribution, which is in the bottom. Yeah, final slide. So this is to, so actually, yeah, so far I just talk about how to learn this like bootstrap word model, but the idea, if you remember, I wanted to do this because actually I wanted to be able to plan over per-chain policy. So what we do in these experiments, we take, for example, FV, we train FV, we have like a parameterized policy by Z, and then on top of this, we train this word model that's now conditioned on Z. So we have like a big parameterized model that predict for each Z what's going to be the future state. And then with that, I can do like planning, and in particular here, I can do like generalized policy improvement to improve upon the per-chain policy. Yeah, and thanks for your time. And this is actually the sorry, and this is actually all the reference I covered in this presentation.
Yeah.